Welcome to Semantic Web Technologies. This is lecture 5, Knowledge Representations, and today we are talking about OWL general role inclusion. General role inclusion means that you will be able to construct complex roles or complex properties from simpler properties, from atomic properties. So, for example, the uncle is the brother of my parents. So you have has parents, has brother, as atomic or simple properties, and by connecting them, you're creating a new property, which is then the uncle. Doesn't sound so complicated, but in the end, there are some restrictions that hold to keep these things decidable and computable that make it much more complicated. And therefore, the stuff that comes now is not for the faint of heart. So this will also not be subject of the exercises, because it's rather complicated and you should have a sound knowledge of formal languages really to understand the subject, why this becomes incomputable or indecidable. But I try to explain it to you. Okay, so in general, complex roles or complex properties means you construct complex roles from simple roles by simply connecting them with each other. Simplest example, for example, the friends of my friends are also my friends. Yeah, you might say, okay, this is not so complicated. You can do this simply by saying that has friend or is friend is a transitive property. Then the friends of the friends are also the friends, and so on and so on. But if you change the sentence slightly and say the foes of my friends are also my foes, then here are two different properties to be connected, and then it gets more complicated, and then you need general role inclusion or general property inclusion. So this cannot be expressed with join D, because here you say that this guy has a friend and this guy has a foe, and therefore this guy must also be the foe of this guy. So in first order logic, it's easily be expressed to say that for all x, y, and z, it holds that if x has the friend y and y has the foe z, then x also has the foe z. So this is pretty simple. But to formulate this in description logic is something else. Let's try to do this first. Okay, general property inclusion for OWL or for Schroik works in the following way. So you will have an RBox expression that says that you can connect several atomic roles that form another more complex role S here in that case. So for example, you can connect has friend with has foe, and this is a subclass or includes has friends foe then. So you have here combined or declared a complex new role that says the foes of my friend, and they are composed from the two atomic roles or two atomic properties has friend and has foe. So in general, you have R1 connected to R2 connected to R sub 3 and so on to R sub n. They constitute the role S. And if you're looking at the semantics of this, it's quite simple. You say that x sub 0 and x sub 1 belong to the interpretation of role number 1. X number 2 and x number 2 belong to the interpretation of role number 2, and so on and so on and so on. And then xn minus 1 and xn belong to the interpretation of role n. Then it also holds that x sub 0, so the very first one, and xn, the very last one, they both belong to the interpretation of the complex role S. So this wasn't so complicated. You can do this also for our example with a has friends foe. So for example, if x sub 1 and x sub 0, they belong to the interpretation of has friend, and also x sub 1 and x sub 2 belong to the interpretation of has foe, then it also holds that the first one, x sub 0, and the last one, x sub 2, has friends foe, or belongs to the interpretation of has friends foe. Okay, so this isn't so complicated, but you know, it's tricky if you look at the details, because you know, in computer science, everything is related. What we have done now with the general role inclusion, we have, of course, extended our description logic. And if you extend the description logic with new functionality and new expressivity, you always have, or there always is the possibility that it might become undecidable. And the problem is, if you use this, just by introducing a harmless thing like that or the uncle, the entire logic will become undecidable. And I will show you how, or I will show you why. Okay. What you have to do for this case is you have to transfer the problem into another area of computer science. So this area will be the formal languages, because whenever you define RBoxes, this is similar to defining formal languages. And maybe you remember formal languages in the Chomsky hierarchy, so you have there these context-sensitive, context-free, or regular languages that are defined via grammars that you see here. And you have here these languages, and here the grammars that create these languages. So you have the language here, and it's defined with two terminal symbols A and B, and on the other end, this is a non-terminal symbol L, can also be defined as A terminal symbol, L non-terminal symbol B, and this L then can be substituted by AB or also by this expression. And this is the same as if you would, for example, define here a role inclusion. You have two roles, are role A and role B, and you combine them and say, okay, this is my language L, and on the other hand, I have the second combination where I say RA combined with L, which is defined here, combined with RB, again, is subset of L. So here you have kind of a recursive definition, and then it's the same like the grammar definition for context-free languages. Okay, so for context-free languages, of course, there exist problems that are not decidable and not computable. So we have to check this. And you can do this. There are two conditions that you might check. For example, you might see that, for example, there always exists a chain RA and RB pertaining to the language. So there must be a chain like this. So this expression holds. And on the other hand, you also can connect this. So for any two languages, L1 and L2, this means there exists a word pertaining to L1 and also to L2. So you can say this in description logics, and you can say this in description logic. And the problem here is, if you say there are two languages, you combine them by combining here language 1 and language 2 in reverse. So you're looking at the inverse of L2, and you connect these two with the same element here. You have the problem that you have to find a word that pertains to both, to L1 and to L2. And you know from formal languages theory that the emptiness of the intersection of context-free languages, so it means a word that doesn't belong to the one and also not to the other, is not decidable. So this is a heavy problem, and it cannot be solved in that way. So it's undecidable, it's uncomputable. Yeah, so we have a problem with these expressions that we can form in description logics if we enable general role inclusion without any restriction. So what should we do? Okay. If you know theoretical computer science and formal languages, then you might remember that there are simpler languages than these context-free languages. And the more simpler languages than the context-free languages are the so-called regular languages. And for regular languages, they have much more simpler or easier construction rules. For them, this problem of the emptiness of the intersection of two languages is decidable. So what we should do is we should consider only those kind of general property or general role inclusions that maintain the condition that they are, if you translate them to a formal language, that they are a regular language and not a context-free language. So we have to think of what are the restrictions we have to put on these expressions from description logic to maintain regularity of the induced grammar that defines a language. Okay. So, with a general property inclusion, this problem is undecidable. Therefore, we restrict now to so-called regular RBoxes. Yeah, therefore, we restrict this to regular languages, and we do this in the way that we say, okay, we introduce a so-called strict partial ordering on the names of our properties that will be connected with a general property or general role inclusion. And then only rules according to these schemata you see here are allowed. So what is allowed in a regular RBox? In a regular RBox, it is allowed, of course, to connect a role with itself and say, okay, this role then is the subset of itself. So you can connect here on the left side these two roles that are also on the right side. This is no problem. Regularity is maintained. On the other side, you can also say that the inverse of a role is subset of a role. This is also regular. And of course, if on both sides of the subsumption sign or of the inclusion sign are not the same roles, so if R does not occur on the other side, then it's also no problem, because then this connection, if S itself is only an atomic role and is not a complex role where R somehow is involved, then this also is a regular RBox rule. The two complicated cases are whenever R occurs also on the other side of the subsumption sign. And there are only two cases allowed, and the first case is R is somewhere right at the front, or R is somewhere right at the end. It is not allowed to stay somewhere in the middle, only on the front or at the end. And more important, all of the other roles that are part of this role inclusion, for them it must hold that they are smaller than R, according to the ordering we have defined. And then, if an RBox complies to these rules, the RBox is called regular, only if such a strict ordering really exists. I can give you a simple example of two rules or two inclusions that are not regular. Of course, they are not regular, but it looks simple. So for example here, we have one has parent connected to with has husband, and this is a subset from has father. So we say the husband of a parent is a father, would say this thing. So this is quite simple, you can do this. The first rule, pretty simple. So here you have nowhere one of the constituents of this role inclusion on the other side. So has father is here and not on the other side. But you have a second rule in the knowledge base, and the second rule says has father, of course, is a sub-property of has parent. And then it becomes complicated, because then here has parent can be substituted by has father, and then we have here, of course, maybe a problem. So this is not regularity, because regularity would enforce both. So from the first rule that we have here, it would induce that has parent is smaller than has father. And from the second one, it would induce that has father is smaller than has parent. And this is, of course, no strict ordering, because this, of course, must be strict. In both, the same order must be applied. And therefore, this is not a regular RBox. Because if you use this, then you will, then it will become undecidable. And then the complexity is too high and computation will not end, probably. So this is a complicated rule. Whenever you try to use this general role inclusion, these rules has to be obeyed. You only can use roles in the role inclusion that obey these rules of regularity. Otherwise, it would be undecidable or uncomputable. So regular RBoxes are restricted to these rules of regularity, and so-called simple properties or simple roles. Simple properties in join D are properties without transitive subproperties. In Schroik D, it's a little bit more complicated because their general property inclusion has to be considered. Their simple properties are properties that are not on the right side of the property inclusion or that are the inverse of other simple properties. Or, this is the last case, they are only on the right side of property inclusions where on the left side is a simple property. So where you have such a simple inclusion, so simple subproperty there that only is consists of simple properties, then it's also a simple property. On the other hand, non-simple properties are properties that are directly or indirectly dependent of property chains. It means of this operator somehow. These are not simple properties. So, several expressions are only permitted for simple properties. Otherwise, our entire knowledge base would become undecidable. So, for example, only for simple properties you can use these qualified number restrictions. You cannot use them with complex properties that are based on general role inclusion. On the other hand, also irreflexive properties and disjunctive properties are only permitted for simple properties. And in the same way, if you use here the existential quantifier with the self attribute, or if you use the complement of an instantiation, this is only allowed for simple properties and not for complex properties, because if you would apply these operations on properties that depend on general role inclusion, then again the knowledge base would become, or the logic would become undecidable. So we want to save decidability. So in short, if you summarize all this, first point is we want to ensure decidability, and therefore the following structural restriction must hold for our description logic Schroik D. So first thing is regularity. It means the RBox axioms, there are certain restrictions concerning the interaction of RBox axioms that deal with regularity. You remember there are only certain forms or certain schemata of role inclusion allowed, and there must be a strict ordering that has to be maintained. And on the second hand, we have simplicity of properties that must also be maintained, because there are several restrictions on which properties in number restrictions, for example, are applied, or on which other procedures and other things are applied only on simple properties and not on properties that rely on general property inclusion, because otherwise we would lose the property of decidability. Therefore, a number of restrictions arise for the overall structure of the knowledge base, and they have to be considered, of course, in all of the axioms. But you must be careful for that, because also it might occur that the union of several knowledge bases might violate these restrictions, although each single underlying knowledge base itself does comply to the restriction. This is also possible. Okay, this was the theoretical part. If you want to know how you do or how you code general role inclusion with OWL, it's quite simple. So for example, if we stay with our has friends foe property, we can say that this new property has friends foe is an object property, and this object property has also here the property OWL property chain axiom, which means here we define a general property chain or a general property inclusion of the following two simple roles or simple properties. We connect has friend with has foe. So this is a property chain, and we allow this for has friend, has foe. And of course, this only holds for object properties. It does not make sense if you apply this chaining to data type properties. But how should you connect data type properties? So this is only allowed for object properties. Okay, so this was the last part of the OWL, the Web Ontology language. So only for this small piece of definition for the property chains, you had all this theoretical computer science stuff with the formal languages to consider, because we have to maintain decidability. Undecidability is a bad thing, then of course computation might eventually not stop, and we try to avoid this simply. Okay. What's next? In the next lecture, we are still on the topic of knowledge representation. We want to look what is beyond OWL. And beyond OWL are the so-called rules. Because you can, for example, describe knowledge that is complicated, much more complicated than, for example, things we have defined in OWL. But on the other hand, is still decidable. And this can be expressed with the help of rules. And there, you must be very clever if you combine both rules and OWL to maintain decidability. But we won't go deep into that. What I want to give you in the last part of the lecture is a slight overview about what are rules, how are rules used, and how can I combine rules with the already known semantic web technology.